For any engineer or hydrologist trying to figure out what happens in a major flood, there's this one fundamental question. When the sky just opens up, where does all that water actually go? And believe me, accurately predicting that flow is one of the biggest challenges in the field.
For decades, the standard playbook has been to split this problem into two separate parts. But what if that's not the best way? A newer technique is starting to challenge that entire workflow, and it promises a much more unified and maybe even a more accurate picture of what happens when the water starts to rise.
Okay, let's break this down. On the left, you've got the classic traditional method. First, you run a hydrology model. Its whole job is to figure out how much water is going to run off the RAND. Then you take that result, the hydrograph, and you hand it off to a totally separate hydraulics model to figure out where that water is going to go. It's like a relay race. But look at the right. This is rain on grid. Here, you just make it rain directly on a digital map of the terrain, and one single program does the whole shebang. It calculates the runoff and the flow all at once. It's a huge shift in thinking. So let's get into the nitty-gritty. What exactly is rain on grid modeling anyway? Well, at its heart, it's pretty straightforward. Rain on grid takes all the rainfall that doesn't soak into the ground, what engineers call excess precipitation, and it applies it directly, everywhere, onto a 2D grid of the landscape. From there, the software just lets physics take over. It calculates exactly how that water is going to move from one little square to the next, just following the natural bumps and slopes of the land. So here's how it works, step by step. First, the model creates the storm itself using something called a hyetograph, which is really just a fancy graph showing how hard it's raining over time. Then, for every single cell in the model, it figures out the losses, basically subtracting all the water that's going to soak into the ground. And finally, whatever's left over gets routed from cell to cell, creating this amazing dynamic picture of the flood as it actually happens. All right, but let's be real. No new technology is a silver bullet, right? Rain on grid is powerful, for sure, but it comes with a pretty big list of pros and some very real cons that every modeler has to wrestle with. So the benefits? They're pretty compelling. For starters, you don't have to spend hours trying to manually draw watershed boundaries, which is a total nightmare in flat areas. It's also way better at capturing weird, complex flow paths, like when a huge storm causes water to spill over a ridge into a totally different valley. Old models just can't handle that. And of course, having everything in one program is just so much simpler. But here's the other side of the coin. To make this work, you need a huge, super high-quality digital map of the entire area. And because the computer is calculating physics for every single little square on that map, the runtimes can be brutal. We're talking hours, sometimes days, of your computer just chugging away. And the files you get at the end, they can be absolutely massive, a real pain to share. Plus, there's still a healthy debate in the industry about how accurate it is, especially for really shallow water that the map data might not even pick up. So you can see how this brings up the million-dollar question for any engineer using this tool. With all these different settings and variables and potential problems, which are the ones that really move the needle? Which tweaks just fine-tune the results, and which ones can blow up your whole analysis? Well, to find the answer, we can turn to this incredible real-world stress test that was done out in Colorado. Yeah, the Colorado Water Conservation Board decided they were tired of just guessing, so they funded this massive sensitivity study to figure out, with actual numbers, what happens when you start turning all the different knobs inside one of these super complex models. The testing ground was the 85-square-mile Trout Creek watershed. It's mostly just forest, pretty undeveloped. The team ran hundreds and hundreds of simulations, and each time they would systematically change just one variable, one knob, to see what would happen. The goal was simple: measure exactly how much each of these little adjustments could change the final flood prediction. And the results? Well, they were a real eye-opener. They highlighted a few key factors that have a totally outsized impact on the final numbers. So they broke all these variables down into two main buckets. On the one hand, you have hydrology. These are the knobs that control the rain itself. Think storm duration, how much rain falls, that kind of thing. On the other hand, you have hydraulics. These are the knobs that control how the water moves across the landscape. This is stuff like the grid cell size and how rough the ground is, which engineers usually call Manning's N. Now, a lot of these knobs made a difference, but there was one single hydraulic knob that stood out with a just jaw-dropping impact on the results. And that was the size of the grid cells you use to build your digital terrain. 55%. Let that sink in for a second. That's a huge number. That's right, no typo there.
On average, just by making the digital map twice as detailed, say going from 200-foot squares down to 100-foot squares, the predicted peak flood flow jumped by a staggering 55%. It was by far the most sensitive knob they could turn. And this table here, it just lays it all out beautifully. You can see mesh size is sitting right at the top with a very high impact. But look at what else is up there. The shape of the storm and something called antecedent moisture, which is basically just how wet the ground is before the storm even starts. Those have a high impact too. And what's really interesting is that the ground's roughness, Manning's N, while it's still important, it's only moderate compared to these other heavy hitters. Okay, so with this knowledge in hand, how can engineers and modelers make better, more defensible decisions when they're building these things? Well, the study gives us some really clear guidance on that. It really boils down to these 4 pillars. First, know your goal. Talk to everyone involved and figure out the level of detail you actually need before you start building. Second, whenever you possibly can, calibrate your model against real-world data from past floods. Third, don't reinvent the wheel. Check your local drainage manuals and see what the established methods are. And finally, and this is huge, document every single assumption you make. So much of this is based on engineering judgment, so being transparent is absolutely critical. You know, this all leads back to a fundamental truth in any kind of modeling, and it was perfectly captured by the statistician George Box, who said, "All models are wrong, but some are useful." No model is a crystal ball. The goal isn't to be perfect. The goal is to be useful. And that, right there, is the crucial takeaway from this whole Colorado study. The thing that separates a useless model from a useful one is understanding its limits. Knowing which knobs have the biggest impact, knowing where the uncertainty is, that's what allows an engineer to use this powerful tool responsibly. So this leaves us with the one critical question that every single modeler has to face. Knowing that one decision, like your grid size, can swing your results by more than 50%, how are you going to balance the temptation to build a super complex model with the actual practical goals of your project? At the end of the day, it's not about finding the one right answer. It's about understanding which knobs you're turning and why.